So let's get back to the Schrodinger's equation. Let's get back to the Schrodinger's equation. So this was kind of a diversion. So let's get back to Schrodinger's equation. Why did I talk about this? Bound state versus scattering state. Because that distinction will also be important in quantum mechanics. Okay? Bound state versus scattering state will also be important in quantum mechanics. And so chapter 5 is devoted to solving Schrodinger's equation in simple situations that correspond to simple bound states. That's why it's called simple bound states. And chapter 6 deals with solving Schrodinger's equation in simple situations that correspond to scattering states. Okay. Again, bound states in classical physics means the particle rocks back and forth between two turning points. So for example, this would be a bound state, this would be a scattering state. Here you have scattering state for all situations, right? Whether the energy is the thick red line or the dotted red line. Here you have a bound state here or scattering state here. Here you have a bound state here, or if the energy was below U at infinity, you will get a scattering state. Okay, so chapter 5 is devoted to bound states. Sorry about the noise outside. There's nothing I can do to it. So Schrodinger's equation is solved. I put it solved in quotation marks because it's not like a one-shot kind of thing. It's analyzed or analyzed somewhat differently depending on whether we are dealing with the bound state or scattering state. Okay, and relax, don't worry. I'm not gonna give you like a general problem and ask you to solve it on the exam. Solving Schrodinger's equation is not an easy thing to do. So we will spend a lot of time looking at each particular scenario. But in general, what one would do is you would look at the problem, you would look at the potential energy, you would meditate a lot over that potential energy and think about what kind of classical motion that potential energy describes. And for sure, you would think about whether it's a bound state or a scattering state. And then you would slowly proceed to solve the quantum mechanical problem. And your solution sort of depends on whether classically it would be a bound state or a scattering state. Okay, understand? If you don't, go back and rewatch what I just said. Okay, so like I said, solution to the Schrodinger's equation approach sort of requires us to know whether it's a bound state or a scattering state. And we will come back to this. We will come back to this issue. For now, let's massage the Schrodinger's equation a little bit in general terms. So in discussing vibrations of a string, I explained what a mode is. What is a mode? Pause the video and just talk to yourself or to a wall, to your cat, to your friend, to your partner. I remind you that a mode, they're also called normal modes. A mode is a very special pattern of vibration for a string on which each particle has the same dynamics, albeit with different amplitudes and maybe with different phases, but different phase relation. But basically, every particle is doing the same as what every other particle is doing. Mathematically, this corresponds to a variable separable solution. Okay, when the motion of the string, being the function of both space and time, separates into a separate function of space and a separate function of time. The function of space can be thought of as an amplitude profile. And I mentioned that although these are very special solutions, a general solution can usually be built out of these special modal solutions, right? And hence the power of these modes. And this will also be true in quantum mechanics. So, okay, recall string analysis. We looked for modal solutions, i.e., y is the vertical displacement of function of space and time separated into function of space and some function of time. Okay, and these are very special solutions. We found that there's a whole ladder of modes: mode 1, mode 2, mode 3, and the spatial solution can be thought of as an amplitude profile. Right? So if you have a spatial solution like that, that's your amplitude profile. Okay, so what do we do next? Okay, remember, what did we do next? We took this general form of the solution. We still don't know what y and tau are. And we substitute them into the equation that describes the motion of the string. Now we're not dealing with the wave equation, we're dealing with the Schrodinger's equation. So what we're gonna do, we will take psi of x and t and attempt to look for modal solutions. In other words, we're going to first try to separate the variables. Now, a standard notation for the spatial part is a lowercase psi. This is uppercase psi. This is a lower case psi. The first time when I taught this class, I had a student who approached me about 2 weeks after this point and asked, why is, I noticed sometimes you write psi with these big bars on the top and sometimes without. Why is that? Okay, so to avoid this kind of situation, I'm telling you that the lowercase psi is the spatial part of the wave function, okay? And the uppercase psi is the full wave function. Okay, is there a universally accepted letter for the temporal part? No, sometimes you just use F, okay? So here's our variable. This is our variable separable form. Okay, now we're gonna sub into the Schrodinger's equation. And when we sub that into the, well, let me just do that, right? So on the left-hand side, I have left-hand side. I'm gonna do two sides separately. I have I h bar, right? So we go to the Schrodinger's equation. You have I h bar times the time derivative. Well, the time derivative doesn't affect this, but it does affect the time derivative of this. Okay, left-hand side. And then right-hand side, sorry, right-hand side. Well, let's look at what the Schrodinger's equation looks like. You have minus h bar squared over 2m times the spatial derivative plus u times psi. Spatial derivative is only going to affect the little psi. So you have minus h bar squared over 2m d squared psi dx squared. Notice that in one dimension, these become total derivative. Derivatives, sorry, plus u of x times psi of x f of t. So this part is basically just going along for the right. It's intact. Okay, and so you equate the two things. Okay, equate. And then divide by the wave function itself. Remember, we used that trick. We substituted the variable separable ansatz, and then we divided the whole thing by the y. Okay, and when we do that, we would get the following thing. IH bar df dt divided by f equals minus h bar squared over 2m d squared psi dx squared plus u of x times psi of x. So here I'm explicitly showing the x dependence, but here I'm not. Well, okay, I can do that. It might look a little bit messy, but that's fine. It's not f times t, it's f of t. It's a function of time, okay? And what you have here is you have psi of x. At this point, you pause. You just freeze, and you stare at it. You stare at it, you stare at it, you meditate on it for about 20 minutes if necessary. And you say, wait a second. The left-hand side is only a function of only time. And the right-hand side is a function of only space. You say, well, how is that possible? Apples equals oranges, right? Where apples and oranges are variable. And that's only possible if both sides are equal to a constant, right? You cannot say that x squared equals t cubed. It makes no sense unless both functions are constant. So if one is 25 and the other is 25, then it's possible to have this constant function being the same function. And so we reach a conclusion that both sides must be equal to some constant. This is called a separation constant. And we can just use a generic letter T. But in foresight, having done this already many times, I'm going to use a letter E, okay? And the reason is that you will see that the physical meaning of this separation constant will be energy. Okay, so this gives me minus I, sorry, not minus, this gives me IH bar df dt, I'm not writing the argument of f, equals E times f. Or I can write that as df dt equals E over I h bar times f. Now 1 over I equals minus I. Why is that? Because 1 equals minus I times I, which is minus times minus equals plus, okay? So 1 over I equals minus I. You can also realize that 1 over I is I to the minus 1. Now I is e to the I pi. So 1 over e to the I pi is e to the minus I pi. I'm sorry, 1 is e to the, sorry, I is e to the I pi. I guess let me say I is e to the I pi over 2. 1 over I equals 1 over e to the I pi over 2 equals e to the minus I pi over 2. Right, so you have a complex plane. So this is I, okay? And this is now e to the minus I pi over 2. You go in the minus direction. This is minus I. So all I'm doing is I'm trying to explain why 1 over I equals minus I. You can just sort of check that this is true, or you can realize that I is e to the I pi over 2, right? So you go 90 degrees, phases pi over 2, 90 degrees. 1 over I is 1 over that, so it's e to the minus I pi over 2 that you go in the negative phase. It becomes minus I. In any case, df dt equals minus I e over h bar f. And you will recognize, aha, if this is energy and this is h bar, this is something like angular frequency, because Monsieur de Broglie told us that. And you will see that indeed this has the meaning of angular frequency. Now this equation is very simple. It has a general solution. It's an exponential solution. General solution is f of t equals some constant e to the minus I e over h bar times t. And again, you see that e over h bar has the meaning of angular frequency. We're done with the temporal part of the Schrodinger's equation. It's very general. No matter what physical situation the particle is in, no matter what potential energy it's put into, if you're looking for modes, if you're looking for a modal solution, the temporal dynamics of the mode will be given like that. And compare with the string. With the string, we had something like cosine of omega t plus phi naught, right? It's basically the same thing, except it's a complex version. In other words, every particle is executing a periodic motion, except that this is a complex, it's a complex sinusoid, but it has a real part and an imaginary part. It's basically the same thing. It's a periodic motion with this additional difficulty that it's a complex, these are complex sinusoids in time. Okay, so this is the temporal part. So this is the temporal equation. What about the spatial equation? Right, so we separated the variables. All right, so on the left-hand side, we have this equals E. On the right-hand side, we have that thing. So the spatial part, which comes from the right-hand side of the separation of variables. Spatial part reads this, minus h bar squared over 2m d squared psi dx squared plus u times psi, both functions of coordinate, equals E times psi. So the left-hand side does something to the psi, right? You can think of, again, this is like an operator. Hitting, bing, it hits the psi. It does something to the psi. It takes its derivative, multiplies the derivative by minus h bar squared over 2m, plus adds the product of u times psi, some weird thing, and the result is you get the psi back, okay? And so now, this is called time independent Schrodinger's equation. This is a big deal. This whole thing is called time-independent Schrodinger's equation. It's a Schrodinger's equation. It's like Schrodinger's equation, but just for the spatial part of the wave function. Okay. So this time-independent Schrodinger's equation. let's just stare at it. So you have something plus something equals E times psi. You will see that the first term, the first glob of stuff, minus h bar squared over 2m times the second derivative of psi, it's basically the kinetic energy of the particle in quantum mechanical terms. And the second term is basically the potential energy of the particle. Or I could say the first term is related to the kinetic energy. We can extract the kinetic energy from the first term. And the second term is like the potential energy. Second, here's the big deal. We cannot proceed to solve this equation until I tell you what U is. Okay, so to proceed, we have to use a particular U. Okay, so if we're solving mass on a spring, we have to use the harmonic oscillator U. If we're solving a hydrogen atom, we have to use the Coulombic U. If we're solving some kind of a nuclear problem, we have to use the U that describes the nucleus. If we're solving some kind of a scattering, we have to U that describes that scattering, and so on. So the physics is in the time-independent Schrodinger's equation. But before moving on and starting to look at examples, so chapter 5 is just chock full of different examples, each corresponding to different U, to different physical situation. But before moving on to these specific examples, let's milk this a little bit more. Before moving on to specific U, a few words must be mentioned about the properties of these modal solutions. Okay, so first, note that psi star psi equals psi star psi, right? Because psi is it's the temporal. Sorry, psi is the spatial part times e to the minus I e over h bar times t. I'm not writing this f naught right here because f naught can always be absorbed in the psi. Okay, so if you say, oh, you missed f naught, no, not really. I can always absorb it in this, right? It's a constant. It's a constant. Okay, and so psi star, well, what you do is you conjugate the spatial part, and then you conjugate the temporal part. And when you multiply one psi star times psi, you get psi star times the psi. Notice uppercase, lowercase, general, spatial. E to the I e over h bar times e to the minus I e over h bar time. So you have e to the I theta times e to the minus I theta equals e to the 0 equals 1. Okay, so this whole darn thing becomes 1. And so therefore you get this thing. So what does that mean? What's the physical meaning of this? Why am I bringing your attention to this? It says that the probability distributions that correspond to modes, right? So if a particle is described by a modal solution, its probability distribution is time independent because this thing is time independent. Okay, so probability distributions right? Remember, probability distribution is given by psi star psi. From modal solutions, only from modal solutions are time independent, okay? And as a result, all the averages produced by these modal solutions, sorry, as a result, all the averages produced by these distributions from each particular modal solution will be time independent. In other words, if a particle is described by the third mode and only by the third mode, if a particle is in the third mode, the probability distribution is time independent, and the averages of all quantities, position and momentum, also be time independent. If a particle is in the fourth mode, okay, the probability distribution for position is time independent, probability distribution for momentum is time independent, and all the averages will also be time independent. And so for this reason, the modal solutions, these normal modes, are often called stationary states. Stationary meaning time independent. These modal solutions are stationary states. Second, just as it was in the case with wave on a string, a general solution can be built out of the superposition of these modal solutions by a sum, also called a linear combination. So general solution can be written as a sum of modal solutions. So the most general solution describing a particle in a particular potential energy landscape, in other words, interacting through a particular force with something, can always be written as a sum, C sub n times the modal solution. I want to write this beautifully because this is very important, times e to the minus I e sub n over h bar times t. Right? So this is a coefficient. It tells you the amount of mixing in of these modes. Okay, so this is kind of a amount by which each mode is represented in the general solution. Just like Fourier sum, okay? Except that now we're not adding up just plain waves, we're adding up modal solutions. So how do you determine these coefficients? These coefficients are determined by initial conditions. Just a fact for you, don't worry. You're not supposed to know that right now, I'm just giving you that as a fact. And just as omegas were discrete, the frequency of each mode, they were discrete in the string solution, and they were dictated by boundary conditions. We will see that E sub n's will also be discrete for bound states, but not for scattering states. And they're also determined by boundary conditions. But for scattering states, they will be continuous. okay? Now, boundary conditions can have various forms. It's not a one size fits all. But there will be, in one form or another, some sort of information about the boundaries, what happens at infinity, what happens at zero, what happens at the wall, what happens at the nucleus, what happens at some location. Just like with the string, the fact that the string had to be pinned at both ends, that forced the frequencies to take on only discrete values, because then the wave numbers would only take on discrete values, and that's needed in order to fit exactly integer number of half wavelengths. Same idea will apply here. Okay, but in a scattering state, E will E's will form a continuous spectrum. Let me use an adult, like a grown-up language. E's will be continuous. So you could say a discrete. You could say that discrete, you can call this discrete spectrum. So the spectrum of energies will be discrete, and you could say that this will be, the energy will form a continuous spectrum, continuous spectrum. And then the sum will be replaced by an integral. Integral over what? Well, that depends again on a physical situation. We will mention some more properties of bound states as we go along. And the next thing to do is to start looking at particular physical situations. In other words, particular use. Okay, we will start, well, first the next lecture, I think we're done for today, but I will remind you what's going on. And then we'll look at what are the common physical situations, i.e. common potential energy landscapes that you're familiar with. And then we will look at some model situations. They don't correspond to anything physical, but they're educational. They're very useful to gain intuition. And the first of these will be called a particle in a box. It sounds silly, but it basically describes a type of situation when U equals constant in between the two ends, and then it's infinite. So it describes a particle that's bouncing around between the two walls. It's experiencing no force in between the walls and an infinite force at the walls that does not allow a particle to penetrate the walls. It's kind of an artificial situation, but it will be surprisingly very useful for building the intuition as we move on further.